In today's video, we will learn what is the relationship between distance and speed, what is the relationship between displacement and velocity, and when should you solve for speed versus velocity. Let's get started. Let's start out by talking about velocity and displacement. Recall from the last video that displacement is how far away an object has traveled from where it was initially located. So in this case here, measuring an object's velocity tells us how fast an object traveled a given displacement in a specific amount of time. So if we were to write that mathematically as a relationship, we would say that velocity is equal to displacement divided by time because it is a rate of change. Okay, when we go to calculate this, in physics, we use the letter t to represent time. So we have a new variable today. The total time an object is moving can be written as delta t, which is equal to tf, or the final time, minus t naught, your initial time. Now, usually t naught is equal to 0 seconds, so we can simplify our time variable to t. Combining these ideas, we get displacement, delta x, time is t. Again, sometimes it's delta t, but oftentimes this happens when you're looking either at a time graph or if you're looking at lab data. So your equation will be delta x divided by delta t, or delta x divided by t when t naught is 0 seconds. Now, in comparison, recall that distance measures the length of a path traveled and does not depend on direction. Therefore, speed is also another way to determine how fast an object is moving. The difference is that it's looking at a certain amount of distance and a given amount of time. So it's still a ratio between those two values, so speed would be equal to distance divided by time. Now, once again, we do have time, and if t naught is 0, you can opt out of delta t. So when we combine these two together, we get distance is d, time is t, sometimes delta t. So you get speed, or s, is equal to d divided by t. Now, let's go ahead and compare the two, because you can see that there's quite a bit in common. First of all, they're a ratio between a length and a time. And because of that, they have the same SI unit, which is meters per second, because both distance and displacement have the unit meters, and time is measured in seconds. The thing that is unique about these two is that velocity is a vector. And the reason why is because it's dependent on displacement. So if your displacement is positive, your velocity is positive. If your displacement is negative, your velocity will be negative. In comparison, speed is scalar because it's dependent on distance and time, which are both scalar values. So speed will always be a positive value, and it'll reflect how fast an object traveled a total distance. Now let's look at the specific case of if displacement is 0 meters. What is the displacement of an object that starts and ends at the same position? This is going to be useful because it brings up a good point, and it really differentiates when you may need to use speed versus displacement. Notice that we have someone on a track. Now, this could be a runner, this could be a race car, but whenever you go on a track, the start and finish line is in the same position. So we know that displacement is our final position minus our initial position. But notice that in this case, our final position is equal to our initial position. So the difference between where the runner started and ended up is 0 meters. So in this case, whenever you have an object that starts and ends in the same position, their displacement is going to be 0. Now, what is the impact on velocity? Well, if our displacement is 0, then our velocity is going to be 0. But that's weird because by definition, velocity should be how fast the runner was moving. Well, we know that the runner definitely moved, right? In fact, they ran a whole lap. However, because they start and stop in the same spot, we don't really get any information because their displacement is 0. So this is one of the reasons why you may need to use speed to determine how fast the runner was moving along the track. Whenever the displacement is 0, you're not going to get information about how fast the object was moving. Let's go ahead and try some examples. Now, these should look familiar because they are the same examples from the last video. The only difference is we've added a time component. A runner begins their journey at the start line located at 0 meters and runs west -25 meters in 5 seconds. So we're going to solve for the runner's velocity and solve for the runner's speed. Just as a quick recall, we got positive, negative, positive, negative for our directions. We're going to start over here. And this position is going to be our initial, which is equal to 0 meters. And then we're going to travel west, which is to the left, and we're going to go -25 meters. Now, the new component to add to our label diagram is the amount of time that has passed, which is 5 seconds. And now we have everything we need to go ahead and solve. So first step is going to be to solve for distance or displacement. In the case of velocity, we're going to solve for displacement, which is equal to our final position minus our initial position. In this case, it's going to be -25 meters minus 0 meters, and that will produce a displacement of -25 meters. Now we can go ahead and plug that in to get our velocity. Velocity is equal to the displacement of the runner divided by the amount of time that they were running, which is going to be equal to -25 meters divided by 5 seconds, and that will give us a velocity of -5 meters per second. In comparison, speed will be a relationship between distance and time. So we're going to solve for our distance first, which will be the absolute value or the magnitude of our displacement, which is equal to the magnitude of -25 meters, which is equal to 25 meters. We will then take that and plug it into our equation for speed, which is equal to distance divided by time. And in this case here, we would get 25 meters divided by 5 seconds. And notice that our speed has the same exact magnitude as our velocity. It just does not have a sign because it's not dependent on the direction of motion. So this is a nice and simple kind of example where there's just one displacement. So the distance and the displacement have a lot in common. And the main difference is the sign of the speed versus velocity. Let's look at a more complex case. Here's a more complex case. Again, this problem should seem familiar. It has all the same pieces, except we've added a time component. So we have a kid that rides their bike 15 meters east, then they turn around and travel 4 meters west. They complete their journey in 12 seconds. So we're going to calculate two things. We're going to calculate the average velocity and the average speed. Now, when you see average in a physics class, what that is asking you to do is look at the total information that you are given. So rather than just displacement 1, like we looked at last problem in displacement 2, we're going to go ahead and get the total displacement and then divide that by the total time. So let's go ahead and start out by labeling this diagram. We're going to start with an initial position of 0 meters. Then at this point, we'll have traveled 15 meters east, which will give us a positive 15 meters. And then we're going to travel 4 meters west. So I'll be subtracting 4. Then we're going to travel 4 meters west, which will be subtracting 4. And 15 minus 4 is going to give us 11 meters. And this is where we will end up. So again, there's two different parts of the displacement, and we are going to go ahead and calculate the average or the total. So starting off, speaking of which, we're going to go ahead and find both of those displacement values. So delta x1 is going to be equal to x1 minus x0. And in this case, this would be equal to 15 meters minus 0 meters, which will give us 15 meters. Our second step will be to calculate displacement 2, which is equal to x final minus x1, which is equal to 11 meters minus 15 meters, which gives us that displacement of -4 meters. And our last step is to get our total displacement, which is the sum of our two components. So delta x1 plus delta x2, which is equal to 15 meters minus 4 meters, which gives us a solution of 11 meters. Now that we have that, we can go ahead and find our average velocity. So we have velocity is equal to our total displacement divided by our total time, which is equal to, oh, I forgot to label my time, t equals 12 seconds here. So we have 11 meters divided by 12 seconds. And you could leave it as a fraction or ratio, but I like to write my answers in decimals so I can compare them a little bit easier. So this is 0.92 meters per second. And notice our velocity is positive. This is because our kid ends up to the right from where they started. Now, let's go ahead and look at our average speed. In this case here, our first step is to get our total distance traveled, which is going to be the sum of the magnitudes of our displacements. So I'm going to get the magnitude of displacement 1 plus the magnitude of displacement 2. Let's go ahead and plug that in. So I'm going to go ahead and put in 15 meters plus negative 4 meters, and that will produce a result of 15 plus 4, which is 19 meters. Now that I have my total distance, I can go ahead and get my speed, which is the total distance divided by the total time. In this case here, that'll be 19 meters divided by 12 seconds, and this will give me an answer of 1.58 meters per second. Now notice in this case, even though we're using the same components to calculate our answers, speed is faster than the velocity. And there's a reason for this. When we're talking about total distance, remember that distance takes into account the entire path traveled. Therefore, when you divide it by that same amount of time, you're going to get a bigger answer to say how fast they were going because they traveled a further path in the eyes of speed. Now, in comparison, velocity just cares about the fact the kids started at 0 meters and they ended up at 11 meters. It's looking at this displacement here, our total displacement. And because of that, in the eyes of your average velocity, it says, well, you technically only went 11 meters in this amount of time, therefore this is your velocity. So this is a really good example to see that speed and velocity aren't always the same because they are taking into account two different measurements when it comes to the length of the distance or the journey traveled. I hope that today's video is helpful for you. Remember that your growth will be found in the journey rather than in the solution. So go out there and try some practice problems, and I'll see you in the next video.